Okay. So, okay, I'm focusing. That was a harsh introduction. So welcome to my talk about state machines, sometimes a library, always a pattern. About me, so my name is Juliette. I'm a front-end developer at Banque Nationale du Canada. I'm self-taught with a math background. I love TypeScript, React, and functional programming, and poetry and drawing, but that's not for tonight. Tonight is all about state machines. So I will start by making a distinction between logical and physical state management. So by logical state management, I mean the business logic side of things. So pure function which maps one state into another. And by physical state management, I mean the actual implementation of state logic. So that includes the actual implementations, concerns such as storage, persistence, scope, reactivity. So here the focus will be on the logical side of things, which means that although examples will be in React, the main concept will apply to any front-end framework, to some code on the front-end that is not directly tied to the GUI, and to code on the back-end. So I'll situate state machine into broader contexts. So you have, as I see it, at least you have really two ways of updating a state, by events and by value. And those two ideas are well captured by two React hooks, so use state and use reducer. So technically, you can implement each one with the other. So they do have the same potency, if you will, but they do capture different intents. So let's start by updating by value. So as its name indicates, it means that you just send the next value. Wow, that's such a great concept. So what does it mean? It means that you can move from any state to any state. You don't want to restrict the transition. So there's a symmetry between the state that you get and the state that you send. That's the same typing. And that's if there's actually quite much to explore in this. Like I have a talk about functional optics, which really it looks like there's nothing, but there's a lot to it. And the typical situation you're dealing with by updating by values are like dealing with a form or complex query object. But that's not for tonight. Tonight is for updating by events. So what does that mean? It's an idea that you will meet by using the use reducer hook, and it's really at the core of Redux with action. So instead of sending the next state, you send an event or an action in the terminology of Redux. So let's say you have these traffic lights. They can be green, yellow, and blue. I don't have a driver license. So, and you send next event and it changes. So you have a strong difference between the type of events and the type of the states. Like there's no overlap between the value. Also, you can notice that when you send the same event twice, it can yield different values depending on the previous state. So the goal when you're using update by events is to restrict the possible transitions. Instead of having any state that can go to any other state, you restrict it to what is making sense in your application. So you have that in Redux, as we've said. In React, you have the use reducer and the newer hook use action state, which despite its name sorts of acts like a reducer. System is quite focused around this concept. And in the Jotai world, you have the atom with reducer. And the best typing experience, if you want to have a generic reducer workflow, it would be a xstate star and to send XS, which is just like a clone of xstate star in the Tustan world. And I've done my own one because. But so state machine are a peculiar case of reducer. It's one special way of doing it. So I'll start with an example. We will refactor a simple loading element. You have two states. That's quite classical. You might have seen that example before. So the loader can be in a loading state can be true or false, and error state can also be true or false. So there are two things which are wrong with this. First one is if you just look at how we've defined the state, it's possible that the state will be in a loading state and loading true and error true, which doesn't make sense. Like you don't want your application to be in that state, but we're allowing it. The other issue is there is a certain order in which the states can happen, where we can pass from loading true to loading false, but we cannot. It doesn't make sense to go the other way around. And error is the same thing. You can pass from no error to an error. And by just using states and updates by value, we're not expressing this either. So to know which are the progression of states that are allowed, you would have to inspect all the handlers inside the application. So in some way, the business logic would be dispersed instead of being just here collocated with the definition of the state. So state machine will address that concern. So instead, we're refactoring this. So now we have three possible states: loading, success, error. So we have solved the issue of having something which would be both loading and errorful. And we have two events. So when we start loading, either success happen or error happen. And then we define the transition graph. So loading, error, and we have we gave the same names to the state and to the events, so it's simpler that way. So, and implementation is quite simple. So it's that simple because these share some symbols. So we have an initial value and a reducer function. So it's just quite trivial. It accepts a state, an event, and it gives back a new state. So this is how we define a reducer in general and a state machine with those two, a value and an updating function. So yeah, it's a finite state machine. By finite, you see there are like three possible states, 1, 2, 3. Why does it matter? So we've replaced multiple flags that do not freely combine with like three states that there's no possible contradiction. We've expressed a succession of ideas. It was that succession wasn't expressed by the simple value representation. We're regrouping all the business logic, which was both in handler, in state, and state all at the same place. Yeah, the finite part is interesting. It allows you exhaustivity. Because there are a finite number of states, you can like take your time to look at each one. And it's because it's finite, you can also draw nice graphs. And the point is visual communication. It helps to speak with non-dev, with domain experts, which I think is super precious. But it's limited. Finite state machine, you guess it, like having a finite amount, that small amount of information makes something impossible to represent. So we're going to, okay, now another example, turnstile gate. We still have these. Yeah. So let's have a demonstration. There is our turnstile gate simulator with, so it can be either locked or unlocked. And we have two events where either we pay or we push. So, wow. You know, I'm a pro developer. Okay. Now, you all want to know my secrets. How did I code something that's extraordinary? I'm going to show you. So here again, we do an initial value and a reducer function. So two states, locked, unlocked, two events, pay and push. It's a pure function, meaning that if you invoke it twice with the same value, you get this same result. So that's needed, first of all, because we're using a use reducer hook later and React wants this, but the real reason is because it's simpler to reason about this. So we're always using pure function while doing state machines. So there are two nested switch statements. I'm going to lower this a little bit. So you see the outer switch statement is about the state, and the inner switch statement is about the event. And that's really a key when you're thinking in state machine. You think of a state first, and then for each state, you think about the events. The other way around doesn't make you as smart. It's really important to do it that way. And the other switch statement, there is no default value. This is because we want exhaustivity. We want to handle each and every possible state. But the inner switch statement do have default everywhere. This is because we want extensibility. That means we can add new kind of events as our application grow. And so when it's not handled, it means that given state just do not react to that event. So there's a assigned default behavior. Yeah, an interesting thing, like something I call cohesion. Like you have logical consistency, but this is more about like, does it make sense from a human perspective with knowledge of the world? Like, so for example, if it's in a payment state, it doesn't make sense. It wouldn't make sense that you could push the gate. So you understand that because you're a human with some the domain knowledge. And I think this is precious because as developers, we have tons of tools to deal with logical consistencies like type systems, but we have fewer tools to deal with cohesion and human reality. And state machines happens to be one of these. Okay, so here we're just binding what we've defined earlier on. Yeah, no, we are binding what we will define. So thing is, here we have this like floating in space state machine. How do we make it happen in React? So you see this is the component. You have a hook, a custom hook that we will define in the next slide. And those two buttons, there will be like their value and whether they're enabled or disabled. Sorry, their handler and they're disabled. So here it is. So we have this hook. use turnstile. So we have a use reducer with state and send, and here are the the value and the function that we have defined earlier on. So it happens to be really same signature as the use reducer hook without any surprise. So pay will be a handler that it's just a binding to the send method and a pay event. Push with the push button is the same thing. So it's trivial, and it's why it's good. So the value is in here. And here there's something which I think is interesting. So can pay is used to disable the button when it's not relevant. So what we do is that we have this reducer function that we've defined, and we call it, and then we check the result, and is it the same result as before? So why do I like to do? We could just have a condition like if it's in a paying state, then it can pay. If it's not, it cannot. But we would start to disperse the business logic once again. But here, by reusing the reducer function, we're making sure that the can pay method has zero knowledge of the transition graph. So, okay, let's make it, no, that's another application. That's a timer. That's demonstration. So, poof, the time is, and then we can stop, we can reset, we can run. Okay, you get it. You have used these before. So here's the graph. So we have the reset event are self-transition. So they're mapping from a state to the same state, and we have a toggle event. But here, what's interesting, we have this, the state now is a type, as we had before, but also a payload. So some kind of information, some type of qualitative information, quantitative information. So that's why it's an extended finite state machine. That part is finite, and that part is, well, technically finite, but you get it. That part is infinite. So let's look at the implementation. So the states are, you have two possible states, once again, stopped and running, but then you have elapse and since. So the typing of the state is different. The payload has a different type depending on the type of the state. And we have two events and with a now parameter. The reason we need the now parameter is to make sure we're still having pure function. So if not, calling the same method twice would have different results depending of the time, if it was reading directly the time. So the initial state is stopped and elapsed is 0. And then we have two switch statements. So basically, reset is the simpler to get. It's just when we're stopped, it's just sending elapse to 0, and run, and the toggle when we're stopped. Like, yeah, I should define. So elapse, so since is just a fixed reference point. It's the time where we started the timer, but we offset it. Let's say it's 3 seconds has passed. We offset it by 3 seconds. It's not really important, but you just get the idea that you don't compute the things the same way depending on the state. Okay. Next. So, yeah, we have to display the time on the, if we're getting back here. So this is the function that calculates that number. it's the count function. So it's taking the state and a now parameter, which is just the clock. And what I want to bring is that you don't calculate the time to be displayed in the same way depending on whether it's stopped or running. So we define both here. So it's some kind of getter function that works on all the states of the state machine. So once again, we have our little hook that will be that we will bind in our component. So toggle just is sending toggle, but with the now as an extra parameter. Reset, same thing. So it's extended. So both the state and the event do have some kind of payload, and count is the value we get from the count method. And yeah, this one next. So you see the label here does change. So I really wanted to be strict about having no business logic outside of the state machine. So I'm doing kind of the same idea as I was with the can-pay method. So I'm using the reducer, I'm sending an event, and I'm checking which will be the next state. So idea is it will evolve well because I'm not dispersing the business, the logic outside. And no, so I have a little use now hook. I would be actually better with using a use syncing external state, but I did it the old way. And you have a little translation from state to labels, and rest is pretty trivial. Okay, next. So let's get back to the turnstile gate, and now we're actually processing the payment. There is a delay. So we need to introduce a new state, which is like when we pay, and then we can get an error and it's locked again, or a success and it unlocks. So you have two sources of events. You have like user event, whether you pay and push, and you have a system event, whether the payment has worked or not. And the point is, from the point of view of the state machine, it doesn't matter. Okay, let's see a little bit how we are implementing this. So there are three states, like payment, you have some like whatever extra information that would be handled by the physical system, and you have the events. So we have once again two nested switch statements. So this is all the same, but what really changed is here we're using a use effect hook that reacts to the state. So if we're entering in a payment state, then we're sending a payment API call, and when it's done, then we use the send method from the state machine to send back the results so that the state machine can react. So I made it simple for a presentation, but of course you should always cancel your effects, which it's not done here. And the rest is just like we're using the hooks very simply. So yeah, so you use effect works great with state machine. Let's add notification. Have you had that great experience of thinking you've paid your fare and then push the gate and being hurted? So we're not going to do that. We will have a payment accepted, or we're lucky tonight. So, okay. So naive implementation would be to do as we did before, to have a new state, and let's see, to have a success and error state, and having effects and sending over other events. I don't recommend doing that. Problem is, success and error are not meaningful. We don't really need our state machine to pass by their events. So I'm calling them junk state. So they're states that are just used to trigger events. So why not like just send those events directly? So we will use basically the same state graph as before, but we will add a new capacity to our state machine, the capacity to send messages. So effects are good for two-way communication. Like the state machine triggered a payment, and the payment triggered a state transition. Where messages are good for one-way communication. The state machine is sending the notification, but doesn't get anything from that notification. So we have, once again, our states that didn't change, our events didn't change, but we added a message type with the two messages that we have seen before. So either error or success, and the amounts of free tickets there is. So we defined once again our reducer, and I wasn't dogmatic. Now it's not a pure function anymore. We're just calling emit whenever we need it. So just because it's way simpler, and state machine library tends to do it that way. For like in a functional language, I would do it otherwise, but in TypeScript, it's good enough. But the problem here is that since it's not a pure function anymore, we cannot use a use reducer. So we have to do a little custom hook. I will call it use machine, with the initial state, and our extended reducer with state, event, and emit function. So, but doing it, we're not coupling the implementation of the emit. Like when we're defining the message, we're not concerned about what the actual message will trigger. The same way that like effects were also a concern separate from the state machine. And so now it's really simple. We're using a use state. As we've said before, we can use a use state to implement a reducer function, and we're sending the events. Very good. So and then we just implement the message listener. So we're just calling a toast function, and we're formatting the stuff. The point is that is not part of the definition of the state machine. So it's something like, it has other concerns. Like if we would change the library that we use to send those messages, or if we were to introduce some internalization, we would not be touching to the state machine, because that's not the business logic per se, it's interpretation. And then we're just, once again, having that hook that binds everything we define together. And that's all for I had to say about the concrete implementation of state machine. So to sum it back, you can have events and messages when you want to interact. So yeah, state explosion. I love that. Point is, if you want to handle like very complex situation with state machine, you will have like usual problem that you have if you want to handle complex situation with big functions or big class. So like in clean code, it's known as like God function, God class. So God machine, meaning you have multiple responsibilities in the same state machine and different abstraction level. So and the technical meaning of state explosion, if think of an application. Let's say you have a toggle button with 2 states, and you have a drop-down menu with 10 states. So we are already with 10, and it multiplies. So you can like quite quickly have an unmaintainable number of states. That won't work. So what are the solutions? Basically, there are 2 ways out of it, which I'll call connecting and composing. So connecting is the most obvious one. Just don't use one big state machine. Use plenty of simple state machine that lives in the same application. Like your framework will be the thing that lets state machine connect. Different state machines can have different scopes. So you can have a state machine that has a global scope for all the application, and you can have another state machine that deals with a checkbox or with a small GUI. So Xstate sometimes use actor model to have 2 state machine communicate with each other, and in vanilla React you can use reducer and use context to play with the scope. And the other way is composing. Composing means that you have some kind of mathematical operation, abstract operation, to take the small state machine and construct a bigger, more complex state machine. So you still have from your primary state machine, you have like simple things, simple concern, and they only get complex while you're binding them. So in the Redux world, they were big of having one single source of truth. I'm not a big fan of that design pattern, but if you want to do this, like they have their slice pattern to just like think of small reducer and combining into a bigger one. So in state machine, you have an equivalent, which is a product machine. And I'm not going there, but intellectually, I still find it quite interesting to have like some machine, hierarchical machine. You have really lots to explore if you want to go on in this way. So it has been used a lot in embedded system, where they wanted that the whole application was a single state machine. So in that context, when like state charts, which is like some kind of diagrams around these ideas of product and sum and hierarchy of state machines. So states, when they developed that formalism, the idea was to do some kind of visual programmation in the 80s and do a embedded system, the whole application as a state machine. So I'm just like evoking it because I think it's interesting, but I don't feel that it's something that I need that often when I'm working in React. But you might need it. So use cases, like there's one there's a Zag. Zag is a UI framework that is reusable across different frameworks. So you have the same component, you can use it in Solid, in React, I'm not sure exactly what they support, but the point is the way they do that abstraction is they design state machine. State machine is the reuse part of the code, and then they implement the state machine in a different way in each framework. So it's used a lot in embedded system. And automata meaning, a promise, or if you have like a fetching function that have to go through lots of steps and condition, that's a frequent use case of state machines. So there are some libraries that are made to implement state machines. So so far I've presented state machine as a pattern, and I think it's good enough. There is no learning curve. It's kind of false because like you're experiencing that learning curve, but there's no if you know React, you can understand the code about the state machine. So, and you don't have to add extra dependencies. But there are a few libraries. So the most well-known is Xstate. So it's quite big. So I'd say it's an industry standard. There's like super good developer tools. So you can have diagrams that correspond to your code, and you can modify the diagram, and your code will be transformed too. One drawback is that like it's separate of React. They have their own reactive system, and then it's synchronized with React or with Jotai. And it's not a big thing, but I don't like that kind of redundancy. And you need some tools to test your state machine because they're not pure function, because they have that reactivity system. So it's great that they have these tools, but they're solving the problem they've created. But to me, the biggest drawback of Xstate is that the pattern that I've shown you, that there is a state type and a payload, and that the type of the payload varies different depending on the state. Instead, they have a context. A context is just a value that is tied with the state machine, and the typing of that context doesn't change according to the state. So you cannot catch as much logic in the typing. So in JavaScript, that would have been okay, but we're really leaving some money on the table in the TypeScript. And there's smaller libraries, robot with the same problems as Xstate, but smaller. And my own, which is really toy project, so it's pre-alpha. Like, don't use it at your job unless you hate your job and you want to be fired. But you can look at the code. Like I'm still quite proud of it, and I've got some integration with Jotai because I love Jotai. Yeah, this is just a bonus slide. So let's get to the question, and if it's relevant, I'll bring it. Thank you. Et puis, bien sûr, vous pouvez poser des questions en français. Oui.
Les exemples que tu as montrés, genre, sont tous en value, mais en théorie, est-ce que tu pourrais les faire en genre type level?
Tu veux dire que le système de type déterminerait quelle transition peut se faire? Ouais, c'est les Generalized Algebraic Data Types que ça s'appelle. Moi, je trouve que la complication en vaut pas la peine, mais oui, c'est
possible, right?
C'est le sujet d'un autre talk complètement. Oui, mais ouais, Generalized Algebraic Data Types, oui.
Tu as dit qu'au top level, le switch, tu fais le by state et ensuite tu fais le event.
Oui.
Il y a comme une raison spécifique?
Oui, je me suis posé cette question-là pendant longtemps parce que pour moi, c'était clair que c'était la bonne façon de faire. Puis je me demandais pourquoi. En fait, c'est très circulaire. La question, c'est quoi un state? Pourquoi tu décomposes en state? Tu décomposes, un state, c'est les conditions qui vont réagir de manière cohérente à des événements. C'est comme déjà dans ta notion de state. Oui, c'est vraiment c'est pas une raison technique, c'est une raison humaine. C'est que quand tu as décomposé en state, tu as déjà implicitement regroupé par élément. Oui?
In one of like the earlier slides, you talked about going from like a loading state from false to true.
Yeah.
And you said that we would never want to go back from loaded like true to false. But like, let's say you're working with like a dynamic component.
Yeah.
Where you kind of need to like refresh something. Like, is it a bad practice to go back to the loading state of true, or would you just need to like unlock the component?
Yeah, but I mean, in that basic modeling of a loading event, you would never go back. But I mean, maybe there's a special design where you want to do something else. But if I was like in Tanstack where there is a fetch then revalidate, were you thinking about this? Yeah. So what I would do would be a third flag if we're doing in that bad flag style. I would do a third flag reloading, and then it would go. It will just update because you don't want to have a glitch. You don't want to disappear and reappear. But then, like, you would still only go from loading would still only go from true to. Yeah, maybe loading, you would have a loading and error. And yeah, loading could go both way, error could go both way, and you would have like I'm re-implementing React Query on the spot, but yeah, it all depends on what you're modeling. Like in this case, I was modeling a super simple fetcher, but of course you can always find a situation where loading means something slightly different and it makes sense. Yeah?
You mentioned having a single source of truth.
I just think it's not a bad thing per se, is that the extra it's just unneeded coupling. Like there's there is some work to stuff all those things in that single event, like you have the slice pattern and all, but also like it means a giant state. You cannot just have like different modules that have their own concern and are unaware of. Like to me, the main reason to have a single source of truth is because you want to have developer tools and a time traveling debugger. So if you like that, then it's worth it. But it's not because it's a better application design from my point of view. Like, yes?
Ça a été quoi ton feedback, ton expérience dans un contexte de travail à avoir appliqué les state machines pour régler des problèmes complexes? C'était quoi l'effet sur les codes, le bug, la rapidité à régler des bugs, puis l'adoption par les autres équipes et des collègues?
Honnêtement, dans mon contexte actuel, je suis vraiment un pion, puis j'ai pas la chance depuis que je suis deep dans les state machines, j'ai pas eu encore. Mais c'est drôle parce que dans un meeting récemment, quelqu'un avait vu le talk de Nico sur Nicolas sur un sujet assez semblable par rapport au tag onions. Et puis, qui l'ont rapporté dans mon milieu de travail, mais on ne l'a pas encore vu dans le code. Non, mais j'ai pas eu la chance encore. Mais je sais que dans mes applications, là, dans mes side projects, j'ai simplifié des choses très clairement. Si d'autres personnes ont des expériences avec les state machines, I'm not the single source of truth. Oui?
Dans la dernière slide, quand tu as évolué, tu parlais d'optics. Est-ce que tu peux résumer brièvement
Ouais. So, c'est de la programmation fonctionnelle. C'est l'idée que tu as mettons que tu as un objet, puis tu veux updater un champ. Tu veux updater, fait que tu as une fonction qui update la valeur d'un champ en place, puis tu as une fonction qui te donne la valeur d'un champ. Fait que c'est cette paire de fonctions-là qui satisfait certaines conditions, mais tu pourrais aussi avoir une paire de fonctions pour tu as une température en Celsius, puis tu veux lire et modifier la température en Fahrenheit. Tu peux avoir un array avec des strings, puis tu as une fonction qui te retourne un boolean selon si Québec est ou n'est pas dans la string. Puis si tu mets la valeur à true, ben ça s'assure que la string... Fait que tu peux... puis tu peux les composer entre eux. Fait que tu peux, par exemple, avoir un objet avec un champ en Celsius et l'updater en Fahrenheit. Puis tu peux... C'est la composition qui est magique dans ce type d'outil-là. Puis en fait, j'en suis venu au state machine parce que j'ai donné un talk sur les optiques. Puis je me suis posé la question, qu'est-ce que des optiques pouvaient pas faire? Puis je suis allé dans les... Je trouve que c'est tout le temps une question intéressante à se poser avec un outil qu'on aime, à quoi il sert pas.
In certain other languages that feature pattern matching,
Yeah.
I would use that frequently in implementing state machine
Yes.
logic. And I know with TypeScript, there's a proposal and also a library which does that. Have you played with that?
The thing is, like if it was in the language, I would use it, but for implementing a state machine, it's not useful for a very specific reason. So the states are a discriminated union, meaning that you only have to match on the type field. And the rest of and pattern matching, you can match on any field, on any combination of field. You can match if there is an event with an odd number as the time. So. And you just need to match from the type part of the state.
Wouldn't necessarily make it much simpler then.
Yeah.
Bon, merci beaucoup.